ToxWise Academy. Knowledge, analysis, impact.
In forensic toxicology, cyanide presents a massive physical paradox. It kills a human being in a matter of minutes, leaving the victim with this highly unnatural, cherry red complexion. Yet, as a volatile gas, the poison routinely evaporates from the biological evidence before the medical examiner even arrives at the scene. Finding the source of the poison rarely narrows down a suspect list. Cyanide salts are widely used in heavy industries like metallurgy and electroplating, while natural cyanogenic compounds are found everywhere from bitter almonds and apricot kernels to cassava plants. Once ingested or inhaled, the mechanical efficiency of the poison is terrifying. Early symptoms like dizziness and a rapid heart rate accelerate quickly into severe dyspnea, convulsions, and eventually total cardiac arrest. The rapid onset of death makes it nearly impossible for paramedics to intervene in time. And because the chemical is highly unstable after death, securing the definitive proof required for a homicide conviction forces toxicologists into a race against the clock. The core forensic challenge is that hydrogen cyanide actively erases its own tracks. It is incredibly volatile and degrades rapidly in postmortem tissue. This chart tracks blood cyanide concentration after death. Within the first 24 hours, the levels drop drastically, plummeting from a highly lethal peak straight down to near zero. Even the poison's most famous warning sign, the distinct odor of bitter almonds, is practically useless in the field. Between 20 and 40% of the human population genetically lacks the ability to perceive the scent at all. By the time a body reaches the autopsy table, relying on the direct detection of the cyanide itself is a losing strategy. To catch a killer using this chemical, forensic science has to abandon the murder weapon entirely and look for a different kind of evidence. To understand what toxicologists are actually looking for, we have to zoom in on how cyanide shuts down the human body at the microscopic level. This diagram shows the inner workings of a mitochondrion. Cyanide causes a state called histotoxic hypoxia. That red shape, the cyanide molecule, targets and blocks an enzyme called complex 4, instantly stopping the cell from utilizing any oxygen to create energy. Because the cells cannot absorb the oxygen, it ends up piling up uselessly in the veins. The victim is fully oxygenated, but chemically suffocating. This high venous oxygen saturation is exactly what causes the blood and the victim's skin to remain unnaturally bright red. If a patient reaches a hospital alive, doctors have to deploy antidotes that act as chemical hijackers. The preferred clinical countermeasure is hydroxycobalamin. It binds directly to the cyanide, forcibly detaching it from the cell. Together, they form cyanocobalamin, which is just harmless vitamin B12, allowing the body to safely excrete the poison through urine and immediately restoring cellular energy. A secondary method involves injecting sodium nitrate. This acts as a decoy. It produces methemoglobin in the bloodstream, which cyanide actually prefers over the mitochondria, tricking the poison into attacking the altered blood instead of the vital organs. Surviving an exposure requires precise, immediate chemical manipulation to intercept the poison before the cellular blockade becomes permanent. But when intervention fails, the autopsy must begin with strict, time-sensitive protocols to trap whatever volatile gas remains. Medical examiners collect peripheral blood and tissue samples in completely airtight containers. They must leave minimal headspace in the vials and refrigerate them immediately to slow the chemical degradation. Because the raw cyanide ion vanishes so quickly, modern forensic chemists pivot entirely. They stop searching for the poison and begin hunting for metabolites, the stable chemical footprints the poison leaves behind as it interacts with the body's natural defenses. This chart compares detection windows. Cyanide drops off fast. The body converts 80% of it into a metabolite called thiocyanate, which lasts much longer. But thiocyanate is an erratic and flawed biomarker. A victim's history of smoking or eating certain vegetables can cause massive, noisy spikes in the data, muddying the forensic evidence. To secure a conviction, toxicologists need a biomarker that cannot be disputed. They rely on a specific molecule called ATCA. Produced when cyanide reacts with the amino acid cysteine, ATCA is chemically indestructible. It cuts straight through the noise. This survives severe tissue decomposition, remaining detectable in heavily degraded bodies and exhumed remains months or years after the cyanide is gone. By targeting stable biomarkers, forensic science neutralizes cyanide's ability to vanish, securing an undeniable biological trail. This split-screen toxicology report represents the modern reality of forensics. A negative test for raw cyanide no longer guarantees that poisoning didn't happen. Here is what we've learned. First, the oxygen paradox. Cyanide doesn't deprive the body of oxygen. It causes histotoxic hypoxia, shutting down the cellular engines and starving the body of energy while it is literally swimming in oxygen. Second, antidotes as decoys and converters. Surviving a lethal dose relies on injecting chemicals that act as decoys or that fuse with the poison to convert it into harmless vitamins. Finally, the power of biological footprints. The discovery of indestructible biomarkers like ATCA means investigators can definitively prove a poisoning occurred, even on an exhumed body, long after the murder weapon has evaporated. Solving a cyanide case requires investigators to correlate the physical crime scene, the paradox of the autopsy, and the chemical ghosts left deep inside the biology. If you found this breakdown of forensic toxicology helpful, please like and subscribe for more deep dives into the science of investigation.